Okay, we're going to talk about action potential now. An action potential is a sequence of rapidly occurring events that decrease and eventually reverse the resting membrane potential. So you may hear of terms like depolarization and repolarization. Okay.
Minutes or less. In this installment, I will discuss the action potential. The action potential is a momentary reversal of membrane potential that is the basis for electrical signaling within neurons. If you're unfamiliar with membrane potential, you may want to watch my video on membrane potential before watching this video. The resting membrane potential of a neuron is around negative 70 millivolts. When neurotransmitters bind to receptors on the dendrites of a neuron, they can have an effect on the neuron known as depolarization. This means that they make the membrane potential less polarized or cause it to move closer to zero. This chart shows membrane potential on the y-axis and time on the x-axis. When neurotransmitters interacting with receptors causes repeated depolarization of the neuron, eventually the neuron reaches what is known as its threshold membrane potential.
So threshold is this minus 55. Okay, I want you to notice the numbers that you have on the y-axis. These are very important. So minus 70, what we see right here, the straight line, that's RMP, resting membrane potential. Now, something had to have happened to make this become a little bit more negative, a little bit less negative. Or I could say it's moving in a more positive direction, right? Because it goes negative 70, negative 69, negative 60, negative 55, negative 50, blah, 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 all the way to zero, and then you become more positive. Okay, so this straight line is a resting membrane potential. Something had to happen for this to become a little bit more positive. And what's happening is that sodium was rushing into the cell. Some sodium rushes in. When lots of sodium rushes in, you get this incredible spike. When sodium doesn't rush in, but potassium starts to exit, then you start to get this shift going back down. So you have this depolarizing curve and then a repolarizing curve. And when it dips in a more negative direction, more negative than the resting membrane potential, right? If I were to draw this line straight out, we'd be here. But this drop became more negative. That's because the potassium channels are slower to close. So more potassium leaks back into the cell, right? And as a result of that, we get more negative. So sodium is rushing in here, and potassium is starting to exit, right? It's going from inside the cell to outside the cell. And as you get that escape of potassium, it hyperpolarizes. Okay, so let's take a look.
In a neuron with a membrane potential of negative 70 millivolts, this is generally around negative 55 millivolts. When threshold is reached, a large number of sodium channels open, allowing positively charged sodium ions into the cell. This causes massive depolarization of the neuron as the membrane potential reaches zero and then becomes positive. This is known as the rising phase of the action potential. The influx of positive ions creates the electrical signal known as the action potential, which then travels down the neuron. Eventually, the action potential reaches its peak. Sodium channels close and potassium channels open.
That's important. So sodium channels are open here, which allows the sodium to rush into the neuron, changing this voltage, and it starts to become more positive, right? Because you have sodium, Na plus, sodium rushing into the neuron is going to make it more positive. But once it hits that positive 30, depolarization ends, the sodium channels shut, but now you got potassium channels opening. And it's the potassium channels that are quick to open but slow to close is why we start to dip and move more in a negative direction.
Which allows potassium to flow out of the cell. This loss of positive potassium ions promotes repolarization, which is known as the falling phase of the action potential. The neuron returns to resting membrane potential, but actually overshoots it, and the cell becomes hyperpolarized. During this phase, known as the refractory period, it is very difficult to cause the neuron to fire again. Eventually, the potassium channels close and the membrane returns to resting membrane potential, ready to be activated again. The signal generated by the action potential travels down the neuron and can cause release of neurotransmitter at the axon terminals to pass the signal to the next neuron. Welcome to
Okay, that's an important video.
I simplistically
So it'll be important it'll be important
I will discuss the action potential.
to review that a few
The
times.
action potential is a momentary reversal of membrane potential that is the
Okay. We're going to go through that a few times without video. I'll just explain it to you a little bit more. So right here, if we look on the top left, we have what's called a resting membrane potential, which is minus 70. But then something happens and it becomes more negative, right? We're going from minus 70 to minus 80. Remember, when it becomes more negative, we call that hyperpolarization. It's when the membrane becomes more negative. When we're at resting membrane potential and it starts to move in a more positive direction, that's called depolarization. So let's take a look again. This is what that video was explaining, and let's see if we can try and make it a little bit more clear and use that repetition model to help you understand what's happening. So minus 70, that's called resting membrane potential. And what happens if this is a neuron and we have sodium out here, and this is let's say this is a sodium channel, when this sodium starts to go inside into the channel, all of a sudden, the membrane potential starts to change. And because the Na plus, right, Na is a positive charge, when that starts to move inward a little bit, even though we have a negative charge inside, it starts to become a little bit more positive. So from minus 70, we start to become a little bit more positive. Maybe it goes minus 70, minus 69, minus 65, and then maybe more sodium starts to come in, minus 60, more sodium goes in, now it's minus 55. Now, once minus 55 hits, remember, if this was a channel, there's like a gate on the outside, and then there's a gate on the inside. So let's say here's the cell membrane. This is the cell wall. This is the channel, and there's two gates. So some sodium comes in, and it's coming into that first gate until we hit minus 55. Once minus 55 hits, the second gate opens wide open, and it starts to rush way into the neuron. As lots of sodium rushes in, it's not this little subtle increase. All of a sudden, boom, right? Both of these gates are open. You get this incredible positive voltage change. That's depolarization until we hit that positive 30. Once we hit the positive 30, right there, you get the sodium channel closes. Here, the sodium channels are way open. Here, the sodium channel is a little bit open, just a little bit, until it hits minus 55, right? Once minus 55, which is the threshold, once threshold is hit, both of these doors open and sodium goes from extracellular all the way to intracellular, and boom, you get that depolarizing, that rising phase to positive 30, at which point in time the sodium channels close. Now, once the sodium channels close, then our potassium channel opens. And when the potassium channel opens, what you get is potassium going outside from intracellular to extracellular. And what ends up happening is, as these potassiums move outward, now we start to become a little bit more negative. And since the potassium gates are a little bit slower to close, this is going to keep on dipping, dipping, dipping until the potassium channel finally closes. But because they close slower and not as quick as the sodium channels close, it's normal to dip below resting membrane potential. So it's going to dip a little bit more negative. And after it dips and hyperpolarizes, what ends up happening is that's where the sodium potassium pump that requires ATP, that's where it kicks in to restore it back to RMP, to resting membrane potential. If you notice here, it says absolute refractory period, and it looks like that's the green and peach phase. So everything from here to here, when this is happening, you cannot have another action potential that is generated when you're in this phase. Okay? The only time another action potential can be generated is when you're in the voltage, when you're in this phase here, when the voltage gated potassium channels are open and the sodium channels are in the resting state. When you're in this relative refractory period, right in here for sure, this is where if the stimulus is strong enough, you can have another action potential. But if the sodium gates are still open, you can't. The sodium gates have to close, both the activation and inactivation gate. What that means is when you have, let's say this is the channel, and then this is a gate, and then this is a gate, so it has two gates. And if this is the cell membrane, this first gate, they call it the inactivation gate, and the second gate is the activation gate. So in your books, you'll hear inactivation gate or activation gate, open or closed. When this one is opened, when the inactivation is opened, that's what lets some sodium in, enough to reach threshold. But once minus 55 or the threshold is met, then that one, the activation gates open and the sodium can rush all the way intracellular. Okay, so this is the curve that takes place with an action potential. And what you need to be familiar with here is the minus 70, which is resting membrane potential, the minus 55, which is threshold, positive 30, which is the peak. When you're upswinging past threshold all the way to positive 30, that's depolarizing. What's happening in depolarization? Sodium channels are open, right? If you look here, the voltage gated sodium channel activation gates are open. Then right here, the sodium gates are starting to close You can see in the peach color, the voltage gated potassium channels are open and the sodium channels are inactivating. So they're starting to close. Okay. So once the sodium channel closes and we start to move in a more negative direction, or we're approaching resting membrane potential again, right? When you're depolarizing, you're moving away from action potential. You're moving away from resting membrane potential in a more positive direction. When you're repolarizing, you're moving closer to resting membrane potential in a more negative direction. Hyperpolarization is when you're moving more negative in relationship to resting membrane potential. So this is what you're seeing here, some sort of chemical or mechanical change, right? A chemical or mechanical sort of stimulus created this graded potential. So that means it allowed, if this is the cell membrane wall, and you have your channel here, here's your inactivation gate, and here's your activation gate. This is extracellular, this is the cytosol. When some sodium comes in here, right, it exits here, but it moves in the cell membrane. This is when you go from -70 and you start to move in this direction. But not too quick, right? It's a slow bump up till you hit threshold. Enough sodium comes in where you hit threshold, that's when the activation gate opens, and now all the sodium rushes in. That creates that huge upward spike. Then the sodium gates start to close over here. When the sodium gates close, the potassium starts to open, and that's when you start moving this way in a more negative direction. Once we move past the resting membrane potential and you start moving down in negative direction, that's repolarizing. That's because what's open? The potassium channels are open. And here, they're closing, but not fast enough. And that's why you drop slightly below resting membrane potential. This is resting membrane potential. And when it restores, that's resting membrane potential. But this downward dip, that's more negative than resting membrane potential. The absolute refractory period is this phase here, which is where even no matter how strong the stimulus, another action potential cannot begin. The inactivated sodium channels must return to their resting state before they can reopen. The only time another action potential can be started is in the relative refractory, not the absolute. Just remember, absolutely not, right? In the absolute refractory period, you cannot generate another action potential. But in the relative refractory period over here, with a super threshold type of stimulus, you can initiate another action potential. That's because the sodium gates are closed. You have to wait for that to happen in order for another action potential to be generated. So in overview, the resting membrane potential is -70 millivolts. When you're going from -70 to a +30, that's called depolarization. Repolarization is when you're going from +30 back to -70. What is it called if we go from -70 to -90? That's called hyperpolarization. Hyperpolarization. Why does that happen? That happens because the potassium channels are still open. Because they're open, this happens. Okay. Okay, we will pause right here. And when we come back, we'll get into the propagation of action potentials.